This is a chapter looking at convergence and collision. These are the events that give us wonderful mountain ranges like the Andes and the Himalayas. Tall, high, gorgeous mountain ranges that occur because of convergence and collision. At the beginning, we start to look at what happens at a convergent plate margin. One thing we know is that oceanic crust thickens as it cools. This is because as it cools, more rock hardens onto the bottom of it from the top of the mantle, making the crust thicker and thicker. It also becomes denser because as it cools, it becomes more and more dense because, it's the reverse of heating something up, making it expand. Well, you cool it, it condenses, it becomes denser. So even though the idea of, hey, it's becoming denser, so it's taking up less space for the same amount of mass, appears to contradict to the idea that it's thickening, it's getting thicker, it's because it's not the same amount of rock anymore. What's there shrinks and becomes denser, but because it's cooler, new rock hardens onto the bottom of it as it's cooled by being in contact with that cooler, older ocean crust. So that's how it's thickening. Because it's denser than the asthenosphere, it starts sinking into it. And this is the subduction that happens at a convergent plate boundary. As it's sinking, gravity is pulling it. That's why it's sinking, because of the higher density. And that force gravity is exerting on that cooled edge is called slab pull, because that edge of the oceanic crust is the densest, coolest portion. As you get away from the edge and closer to the center where the ocean ridge is, it's warmer and warmer. So the farthest edges are the coolest and densest. They start sinking into the asthenosphere, and as gravity's pulling them down, this is the slab pull that is stretching and pulling it away from the warmer ridge. So early on, this is what we see. We see this ocean plate subducting under this edge of a continent. Now, this isn't the very, very beginning, though. At the very beginning, it's actually usually a transform fault boundary. Something like the San Andreas Fault is an example of a transform fault boundary. And so we have this younger plate moving out of the screen towards you. The older plate is moving into the screen away from you. And it's a generic transform fault. In both cases, it's oceanic crust under the ocean, so this is water above the plates, and this is the ocean crust and the upper part of the mantle making up the lithosphere, and below it we have the asthenosphere. The two plates happen to be different thicknesses. Remember, the older the plate, the thicker it is. So this older plate on the left is thicker than the younger plate. Not only is it older, but it's more dense. So as this transform boundary is sliding along, this older plate can start to dip. It starts going under as it's pulled down. As it's pulled down, it starts pulling towards the middle, and we have a net motion of moving towards each other. So what used to be simply a transform fault has now started to be a subduction zone. Very, very beginning. Hardly anything has subducted yet, but you can see as this gets pulled down more and more, it'll start to look like a classic subduction zone that you've seen in your introductory classes or even earlier in this class. One thing that doesn't usually get talked about in the introductory classes is called rollback. What this is after subduction's been going on for quite a while, so you can see this is the subducting plate right here. Gravity is pulling it down, not along an arc. That's just the direction of motion due to the fact that there's stuff underneath it. It has rigidity. It's going down at an arc, but gravity is pulling straight down. This is, over time, going to actually cause it to change where it's flexing. It's sort of like if you take a piece of paper and you have it sitting on a desk and you start sliding it out over the edge of the desk. The paper will slide out kind of straight for a while and just start to flex and bend downward. But as you get it pressed further and further out over the edge of the desk, more of it is extended. Gravity starts pulling on all of that extended paper, and it changes where the bend is. So at first the bend might be extended a little ways past the edge of the desk, but as you get more and more paper out and gravity pulls with more and more force on the paper, it pushes that bend back towards the edge of the desk. That's rollback. The point of flexure is moving backwards, even though you're sliding the paper out. So, in this case, this subducting plate is moving to the right. However, the point of flexure is moving to the left because of gravity pulling that plate down and displacing more and more of the asthenosphere below it. Because that bend is moving to the left, and we can't just create huge gaps, this means that that accretionary prism and overriding plate end up moving to the left. So, a lot of complex motion going on. A couple of key terms that we've talked about and some new ones, accretionary prism. I've already heard that quite a bit. Four-arc basin and a four-arc and a volcanic arc, terms you've heard before. Plutons, we know Pluton is a magma body that rises up but cools before it reaches the surface. We have the MOHO, the subducting plate here, part of the lithosphere that is mantle material subducting with the crust. Asthenosphere down here, not labeled. Some new terms, though, are outer swell, trench fill, the trench slope break, and trapped oceanic crust. Now, an outer swell, we'll see an image coming up in a couple of slides, but this is actually a rise. It's higher than the ocean crust behind it and higher than the ocean crust that's being subducted. So this is kind of a high point still under the water before the trench. Trench fill is simply sediment that ends up settling down in the trench. So at the bottom of the Marianas Trench there is sediment, and it's called trench fill. This trench slope break is at the top of the accretionary prism, and it's where the direction of slope changes. On the ocean side, it's sloping down into the trench. It's a high point, and then behind it, it slopes down in the other direction into the Forark Basin. This trapped oceanic crust is just basically a little section of basaltic material that was the leading edge before the subduction occurred, and now it's getting pushed backwards and upwards as all of this accretionary prism gets jammed down under it. So this trapped oceanic crust will eventually, if subduction continues until the other continent on the other side of the ocean arrives and slams into it, that trapped ocean crust will end up at the top of some mountain range, even though it used to be the base of the ocean. So in the downgoing slab, this is the solid line is an actual profile. The dotted line is a generic kind of calculated profile if it were acting perfectly elastically. And so here we have the Marianas Trench, we have an outer swell, and we have some seamounts off away from the trench. This outer swell, you can see, is roughly following this elastic calculated profile. We call it an outer swell, or sometimes you'll see it called a peripheral bulge. It's always on the seaward direction away from the trench, and it happens because of the way a rigid but slightly elastic material is going to flex. Oops, I thought my other slide was here. I guess I have it later on. But it's because you have loading on this plate that would have been flat otherwise, and it's causing this upward flexure. When the slide does come up later on, I'll reiterate what this is. You notice this is about 250 kilometers away from the trench. So in this image it's hard to see, but this is a substantial distance away from the Marianas Trench. Now the Wadati-Benioff zone. This is an area where we see earthquakes happening in a specific area. It happens to be along the subducting plate at depths down to about 670 kilometers, and we can use it to see exactly where the plate is. It's defining the location of the subducting plate. It lets us see what angle it's subducting at, and therefore we can see, hey, things can subduct anywhere from a 0-degree angle to a 90-degree angle. So anywhere from basically just sliding straight in under to going straight down. And the dip angle changes along the plate, so it's not that the whole plate is moving at one specific angle. I'll show you what I mean. If we look over here at the Tonga Trench, we can see this kind of cartoon drawing here of a subducting plate. There's the Tonga Trench, Tonga Island, overriding lithosphere, and a bunch of earthquakes showing us where the trench is. I'm sorry, not where the trench is, where the subducting plate is. It's logical for the earthquakes to happen along the plate because the cause of these earthquakes is the plate sliding past the other plate, sliding through the mantle, and flexure and cracking within the plate itself. that's subducting. So all of the earthquakes are going to either be along the edge or within the interior of that subducting plate. If we come over here, we can see 4 images that have lots and lots of dots on them. This first one with the color is an overhead map view of the Tonga Trench area. The colors represent how deep the earthquakes are. So all of these red dots are shallow earthquakes from 0 to 50 kilometers in depth. The green are some intermediate from 50 to 150 kilometers deep. The blue are deep, 150 to 400 kilometers deep. And the magenta, purpley pink are very deep, 400 to extreme cases of 750 kilometers deep. So on average, they max out at around 670 kilometers, but in some cases, special conditions allow a few deeper ones. Then you notice as we move further west, we get back into shallow ones. That's because in this area, if we pop back to the map, we have this trench here, and to the northwest is another trench, and further along more trenches. Multiple subduction zones going on in this region of the Earth. Along a subduction zone, you're always going to see this pattern of shallower to deeper earthquakes as you move away from the trench, either towards the continental interior, if it's an oceanic continental subduction zone, or in this case, it's oceanic plate subducting under oceanic plate. So this is just moving inward along the overriding oceanic plate. If we look at a cross-section, this is the 22 degrees south cross-section, which is this box right here. We can see the shallow earthquakes and then the intermediate and the deep and very deep earthquakes, and we can see a rough shape of a subducting plate here. And it tells us what angle it's subducting at. If we move to the 28 degrees south, we can see here the earthquakes along that profile. Again, the shallow, intermediate, deep, and very deep. And we can see that the plate seems to be subducting at one angle and then change angles as it gets deeper into the Earth. And the southernmost 32 degrees south profile, we can see the plate is subducting at a much steeper angle down there. So we see at different locations along the same subduction zone, the plate is dipping into the Earth at different angles. You think about the fact that we're dealing with a curved surface, so that's going to cause some changes and flexure as you try to take that curved surface and stuff it down into the interior. Plus, the subducting plate is going to have slightly different physical properties at different points along the way. The material it's subducting through is going to have slight differences in composition and pressure and temperature. And so all of this adds up to different conditions and different subduction angles at different places along the plate. Trying to create, if you think about the plate subducting at different angles in different places, that's going to cause a lot of internal stress within that subducting plate, cracking and tearing and bending and flexing as it subducts, which is going to generate even more earthquakes. That's a lot of these earthquakes that you see on the interior of that subducting plate rather than just on the edge where it's scraping past mantle material.